Hello, everyone. In this video, I'm going to continue our discussion of the introduction to AI. In the last video, I talked about the 20th century origins of AI. In this video, we'll talk about the 21st century history of AI. So, first, I want to talk about the difference between AI, machine learning, and deep learning. Because one of the key developments in the 21st century was the development of machine learning and especially deep learning. So, artificial intelligence is the overarching concept of creating machines that can perform tasks that typically require human intelligence, right? So things like virtual assistants and self-driving cars, robots, these are all examples of artificial intelligence. Now, machine learning is a specific approach to artificial intelligence where machines learn from data without being explicitly programmed. For example, spam filters, recommender systems, advertising systems, fraud detection systems, all of these are known to use machine learning. And deep learning is a subfield of machine learning that utilizes artificial neural networks with multiple layers, so-called deep neural networks, to analyze complex data. And its application is in things like image recognition and natural language processing. Now, in the early part of the 20th century, machine learning had developed quite a bit and was being widely deployed and was used by companies like Amazon, Google, and Netflix for things like recommendations, search result ordering, ad placement. In fact, Netflix had a prize that they had announced for of $1 million for anybody who could come up with a recommender system that was better than the system that they were using to recommend movies on Netflix. And that contest was then actually won by this group. These days you have similar contests that go on, things like Kaggle, which is a group that has annual competitions. But this was sort of an early case of such a competition. But the key milestones of AI started with 2011, IBM Watson that beat humans at the game of Jeopardy, AlexNet in 2012 that won the ImageNet competition, generative adversarial networks that were used to generate realistic images, AlphaGo, a software program created by Google's DeepMind that defeated world champion Lee Sedol in Go. AlphaFold, also created by DeepMind, that predicted protein structures with near experimental accuracy. Of course, 2022 saw the development of ChatGPT, which revolutionized conversational AI and text generation, and also things like DALL-E 2 and Stable Diffusion that popularized AI-generated art and images. And then since then, things have been improving, and you had things like GPT-4 in 2023, which offered improved reasoning, safety, and multimodal capabilities. And then finally, AlphaFold 3, which predicted the structure and interaction of a wide variety of biological molecules. So let's go through some of these milestones in a little bit more detail. So IBM Watson in 2011 was an AI system created by IBM, and they came up with this idea that they would use this computer to take part in the Jeopardy contest. Recall that IBM was famous for its Deep Blue machine, which beat Garry Kasparov in the 1990s in the game of chess. And in this case, this was sort of their second major victory, if you will, for AI. And IBM Watson was a system that could understand natural language. And in a way, it was similar to the ChatGPTs of the modern day, except that it was not using some of the techniques that are used by ChatGPT. However, it was figuring out the best way to answer a question. So when it would receive a Jeopardy question, obviously it was able to interpret that question. And then it would use a wide variety of algorithms, natural language algorithms, text completion algorithms, to search for the best possible text to respond with. And it was trained on many games of Jeopardy, many questions of Jeopardy. It had an extensive knowledge base, a lot of different search techniques, and basically it was designed to determine with a high degree of probability what the text would be to respond to a question, right? And that turned out to be so effective that it actually won Jeopardy against these two world champions who had been world champions in Jeopardy for several years. Okay. Now, this is before artificial neural networks really took off. It could be said that IBM Watson was really using more traditional machine learning and natural language techniques. But we should really talk about deep learning, because really the 21st century history of AI is really the history of deep learning. So what is deep learning? Deep learning, as I mentioned earlier, makes use of artificial neural networks for machine learning. So a neural network, a simple neural network, consists of layers, specifically 3 layers. There's an input layer, a hidden layer, and an output layer. What do we mean by these layers? These layers are mathematical objects. So they're basically vectors, right? So input layer is a set of vectors. Hidden layer is another set of vectors. And output layer is another vector. And these layers are connected. And the connections are basically mappings between these vectors, or transformations that take one vector to another vector, right? And these transformations have parameters, right? And those parameters are called weights. And basically, a neural network consists of these transformations that can take an input and produce an output, right? But these weights, or these parameters, are learned. That's what machine learning is all about. In this case, is figuring out what the correct weights should be based on existing data. And this is sort of similar to biological neural networks. Biological neural networks also have these what are called neurons that receive information inputs, and that input, you could think of it as transformations of vectors. And so they receive these impulses, these inputs, and then those impulses are carried away from the cell body of the neuron to what are called axon terminals. And this transmission of the impulse is based on a certain threshold. So if the combination of impulses that are carried towards the cell body exceed a threshold, that's when the neuron essentially fires, and that firing is called a synapse. And that synapse then results in impulses being transmitted to the next neuron through these axon terminals. And this was something that had already been analyzed by McCulloch and Pitts, the two gentlemen who created a mathematical model of the brain. We discussed their work in the first video. And we also talked about the perceptron. So in particular, this perceptron is essentially a artificial neural network, which is a mathematical model of this neuron, where you have these different inputs. So x0, x1, x2, these are all inputs, and those inputs are combined using these weights. This B is called is a constant factor, this combination is then transformed using what's called an activation function. The activation function is a nonlinear function. So if you notice, this combination is linear, right? This combination of inputs is linear, and that linear combination is followed by an activation function. And this activation function is nonlinear, and its behavior is such that it will not do anything if this combination has a value below a certain threshold, but it will fire, simulating a synapse, when its value exceeds a certain threshold, right? So that is the biological model of a neuron, and that's what is called an artificial neural network. A deep neural network is basically a deep stack of hidden layers. So as I mentioned earlier, you have an artificial neural network, which is, what we talked about here was essentially a neuron, an artificial neuron, if you will. And if you take many copies of these, then you have an artificial neural network, and an artificial neural network has an input layer, a hidden layer, and an output layer. Now, if you have more than one hidden layer, that means if you stack a whole bunch of hidden layers, then you get a deep neural network. Now, what are these hidden layers? What do these hidden layers do? Basically, these neural networks, their job is pattern recognition. They're trying to capture patterns in the data using these connections, these neural connections, which are basically mappings, right? And these mappings are basically a linear function followed by nonlinearity. Actually, they're actually a combination, a linear combination of inputs with certain weights followed by a nonlinearity, right? If you just have a single hidden layer, that's called an artificial neural network. In fact, in the early days, people tried to do machine learning using just a single artificial neural network, just using a single hidden layer. If you recall, Marvin Minsky and Papert wrote this famous book on perceptron, where they talked about some of the limitations of the perceptron, so limitations of artificial neural networks. And what was then discovered or realized later on was that those limitations could be removed by having multiple hidden layers. So these hidden layers are learning internal representations of the patterns or the distribution of the data. And those hidden representations are used then in making predictions through this output layer. Okay. So that's a very rough description of what a deep neural network is. Of course, this is quite vague. We will do a better job of explaining deep neural networks. We'll go into more detail and really develop the theory of deep neural networks in a subsequent video. But for now, hopefully this gives you everybody the intuition of what a deep neural network is, right? So starting with 2012, deep neural networks really started dominating the field of machine learning and artificial intelligence. Of course, neural networks and even deep neural networks had been there, had been used for quite some time before 2012, but things kind of came to sort of a head in 2012, where it was a confluence of forces. You had significantly improved computing power. Graphical processing units like GPUs were becoming more and more prevalent. And that opened up a whole bunch of opportunities for training bigger and more complex neural networks. And those more complex neural networks started having a lot of success in various machine learning problems, in particular, computer vision. So in 2012, a deep neural network model called AlexNet, it won the ImageNet competition. ImageNet, it was an annual competition that was held in computer vision, which was to basically classify a whole bunch of images. And until 2012, the image models were purpose-built. They didn't really make extensive use of neural networks. But in 2012, AlexNet was developed by the famous AI pioneer Geoffrey Hinton, who won the Nobel Prize in 2024, who, along with his collaborators, created this machine learning model. He used a special type of a deep neural network called a convolutional neural network. And so that was the model, AlexNet. And it did extremely well in classifying images like these. So basically, you had a stack of neural networks, stack of hidden layers, and there were some special transformations that these hidden layers would go through. And those special transformations would capture all of the patterns in the image. And in the end, you would have a layer whose job was to then use those internal representations to then classify the image. And basically, classification is assigning probabilities for the image. And you can see it would give, it would predict that this was a car with a high probability, right? So that was an early success story with deep learning. And soon after, deep learning also took over NLP, NLP meaning natural language processing. So again, until 2015, all the deep learning conferences, all the conferences in natural language processing, again, we're using very traditional text processing and natural language processing techniques, traditional machine learning techniques. But in 2015, deep neural networks really took over. And after that, um, all the papers, or the majority of the papers in natural language processing, made use of deep learning. And there were several instances where deep learning outperformed all other techniques. These early deep neural networks were um, something called recurrent neural networks. Then there were other algorithms or other types of neural networks like LSTMs and GRUs. And so these types of neural networks were used for machine translation, for example, and they were extremely successful in machine translation. Google Translate, of course, being the most popular example of that, and it made extensive use of these models. And of course, today you have chatbots that use very advanced natural language processing, and of course, they also use deep learning. And we'll talk more about large language models like ChatGPT. So this code is very telling. Deep learning waves have lapped at the shores of computational linguistics for several years now, but 2015 seems like the year when the full force of the tsunami hit the major natural language processing conferences. Okay. So the success of deep learning continued and found its way into game playing. And in 2016, Google's DeepMind created this program called AlphaGo. AlphaGo was a Go playing program. It had been trained using something called reinforcement learning. That's what this RL stands for. Reinforcement learning, which is again a special type of machine learning where you have a system of rewards and penalties using which the program is trained by playing many, many games to improve itself. And reinforcement learning goes all the way back to Samuel's checkers program. But AlphaGo was much more sophisticated than the checkers program, obviously. It not only used reinforcement learning, it also used lots of deep neural networks to make various predictions, to predict moves in the game. And the net result was AlphaGo beat the world champion in Go. And now Go is a game that is orders of magnitude more complex than chess. So while winning in chess or defeating Garry Kasparov, the grandmaster, was a very impressive feat, by IBM's Deep Blue, this was orders of magnitude more complex, more harder, and it used a whole bunch of new techniques, right? Specifically reinforcement learning and deep learning. There's actually a movie on Netflix called AlphaGo. It's well worth watching. And then Google's DeepMind used a lot of the techniques that they had developed in AlphaGo and applied it to other class of problems. And most famously, they applied it to biology. And they used it in predicting protein structures in 2019. So basically, they created these models that could predict using amino acid sequences the three-dimensional structure of a protein. And you see these remarkable pictures of the 3D structures of proteins, these ribbon-like structures. And here's an example of a protein that supposedly protects the malaria parasite against attack by the immune system. Here's another protein that apparently makes a plant resistant to certain diseases. And so there's many such predictions that have been made using AlphaFold, again, which made extensive use of deep neural networks, trained it on many examples of amino acid sequences and protein structures, so that it was able to come up with a predictive model for predicting the structure of a protein. So this work actually won the Nobel Prize for Demis Hassabis, who was the AI scientist who currently heads Google's DeepMind, for his work on AlphaFold. Another interesting development that happened in around the same time, 2014, was the early days of what's called generative AI. So there are these two styles of AI. There is discriminative machine learning or discriminative AI, and then there's something called generative AI. And roughly speaking, discriminative AI's purpose is to distinguish between different classes of data, right? Label data. And so if you want to classify something and you have a bunch of data and you train a model, what it does is it figures out, what is the probability of a certain class label based on the data, right? Whereas generative AI is not really trying to predict the class label. It's not trying to separate out the data based on these class labels, but rather it is trying to figure out the overall distribution of the data with the idea, with the goal of being able to literally recreate similar distributions, right? So the so-called deep fakes, the ability to create fake images that look very similar to actual images, that was the outcome of this technique called generative adversarial networks. And so basically the idea is you have two types of systems. You have two competing systems. One is a generator and the other is a discriminator. The generator's job is to generate a bunch of data, right? Sample data. It starts off with a random input, so it generates random data. And the discriminator's job is to determine if this data matches its distribution with the actual distribution of the data, right? So the discriminator will keep trying to determine that the distribution of the data generated by the generator is off, which will then force the generator to improve its distribution, right? So ultimately, what the generator is trying to do is it's trying to mimic, it's trying to copy the pattern or the probability distribution of the data in the actual data. It's trying to copy that. And to the extent that the copying is not accurate, the discriminator is able to tell the difference. But then the generator keeps tuning itself to make itself better and better and better, so that the discriminator ultimately is not able to tell the difference. And at that point, it's able to generate what looks like the real image. So here's an example where you start off with some random data or random input, you keep tuning it, the discriminator knows what the real data looks like, and it flags it as fake. And then again, the generator improves itself, and then it keeps improving and improving until it's able to generate an image identical to the original image, right? So this is the first example of generative AI. Generative AI is one where it's able to generate as opposed to simply classify data, right? It's not just doing prediction, it's actually generating data. So this is a very powerful technique that was used to generate all kinds of images. And that culminated in 2022 in the current explosion in what's called generative AI. Of course, generative AI is not just using generative adversarial networks. So in the adversarial network, the adversary is the discriminator, right? Who is the adversary to the generator. But there are a whole bunch of other techniques that were used to generate data. So for example, large language models that were used to build chatbots like ChatGPT. And these are models which can generate text. And they generate text by using some sort of a prompt. If you put in a prompt, which is an input, then this model knows how to answer that input, respond to that input with text, right? And the text that it's supposed to respond with, that text is obtained by creating this model. Of course, this model is built by training it against lots and lots of text. And basically, it's a text completion engine. It's basically saying I'm going to take a sequence of text, and then I'm going to figure out what is the best text to follow it up with, right? Actually, technically speaking, it's not just text. It's what's called tokens, but we won't worry about that. For our purposes, these are systems that are trying to respond with text. They're trying to complete the text. And so here's a Time cover magazine about ChatGPT, and it's sort of self-referential because here it says, "Hi, ChatGPT," and it responds, "How can I assist you today?" It says, "What do you think of a Time cover story with the title, 'The AI Arms Race is Changing Everything'?" And then ChatGPT responds, "As an AI language model, I don't have personal opinions or beliefs, but I can provide some context and information on the subject." And then it talks about AI arms race. And that was actually the cover story of Time magazine in 2023. In very similar vein, along the same lines, we had another development, which was something called the so-called diffusion models, which were used to not only generate text, but to generate images. So based on textual prompt, like here's a prompt, a photograph of an astronaut riding a horse. If you gave this prompt to the model, to that diffusion model, it was able to understand the text and it was able to actually generate an image, right? Again, this is an example of generative AI where it's able to actually figure out what is the most appropriate image to generate based on the text. As opposed to doing sentence completion, it's actually figuring out the correct image to generate. Okay, so let's talk a little bit more about large language models. So, everybody's used ChatGPT. Today we have many different very popular chatbots. They've really revolutionized the world of artificial intelligence today. In fact, most people equate AI with large language models, which is probably not, that's not accurate. But these large language models are so powerful and they've become so compelling that when people think of AI, they think of them. So what is a large language model? So a large language model, it's a language model. Basically, it's a model that is able to generate text based on some inputs, right? You give it an input, which is a prompt, and it'll output some text. Okay, so how is this model built? This model is built by essentially taking all of the internet and crawling the internet, grabbing all the text in the internet, um, cleaning it up, filtering it, um, making it safe for consumption, and then cleaning it up, like deduplicating it, and then um, compressing it, essentially taking it and compressing it. And the compression basically is essentially figuring out a probability distribution. It's basically saying, for a sequence of text, what is the best probability for the remaining text? And what it does is it basically chops off a sequence of text. It'll chop off, let's say, the last part, and it'll look at the text before that. It'll try to predict what the next text should be, and it'll compare it against what the actual text is. And then whatever is the error, it'll try to minimize that error by, again, tuning itself, by fine-tuning its parameters so that it can predict, the text correctly. So that's, roughly speaking, how a language model is built. And once the language model is trained, and all the GPU capacity in the world, all the power, all the large data centers, and GPU clusters, all of them are being used essentially to do that, to train these language models, essentially to take all the text, feed it into this model, this algorithm that will train it based on the text to make accurate predictions, right? And the term that is used is, it's a self-supervised learning model, right? It's basically, you just give it a whole bunch of text and then you have it train itself, right? It's training itself using just that text. You're not doing a whole lot of manual labeling or classifying it. Although there is a certain amount of labeling that happens when it comes to conversations, right? But the first step, which is what's called pre-training, that is completely self-supervised, where all you're doing is predicting the next word or the next sentence. But then to turn it into conversations, which is what chatbots do, that's called fine-tuning, and those are actually used. They use supervised learning, where things are manually labeled, or you have humans providing proper responses to prompts or questions, and then the model is trained on that, right? It is taught how to respond properly to these prompts. Okay, so that's what a large language model is, right? And you can see here you have a sequence of what are called tokens. Tokens are IDs of group of characters, if you will, and then it's able to predict what the next token should be, right? Okay, so obviously, ChatGPT, large language models are very popular these days. You have many other large language models like, Claude by Perplexity, Grok by X.AI. Claude is not by Perplexity. Claude is by Anthropic. But there's a whole cottage industry now of companies, startups who are building these large language models, and these models are being applied to build applications. And these models are becoming smarter too. They are becoming multimodal. They are given the ability to search the internet and combine internet search results with the language model. They are also able to do computation, right, or to generate code and execute code. So they're becoming, more and more intelligent. However, at the end of the day, all they are text completion engines, right? I mean, one shouldn't forget that. They don't really have a model of the world, if you will. They can't really understand how the world works. What they're able to do is they're able to capture the distributions of words in text, right? The probability distributions or the patterns of text, right? Okay, so given that we have these large language models, it's a good question to ask, how how do they do with the Turing test, right? Now recall the Turing test from the first video. This was the famous test created by Alan Turing, so-called imitation game, which is meant to determine if a machine is able to think through its behavior, right? Through its responses to certain questions. And if the interrogator is not able to distinguish between a human witness, a human who answers versus a machine that answers, then that would be a definition of a thinking machine. That would be an example of artificial intelligence. At least that was Turing's definition. It was based on perfect mimicry. And it's kind of interesting because when you look at things like generative adversarial networks, again, you have this thing going on where you have mimicry, right? Where you have a system that's trying to mimic another system. So you see that pattern of mimicry come up over and over again. But here, we want to see if a large language model, we want to ask the question, would it pass the Turing test? Well, let's take an example of a Turing test. So this is a snippet of a conversation, which could be part of a Turing test, that is in Turing's original paper, Computing, Machinery, and Intelligence. In that paper, Alan Turing describes a hypothetical conversation between the interrogator and the witness, right? The witness being, it could be human or a machine. So I won't go through all of it, but I'll just give the kind of the brief summary. Basically, the interrogator starts with a poem. It's actually what's called a sonnet. It's actually Shakespeare's sonnet. And this poem starts with this sentence, "Shall I compare thee to a summer's day?" Right? Clearly, it's a romantic poem, right? The poem is, trying to praise or trying to express, adoration or affection for this other person. And it starts off by comparing that person to a summer's day. So the interrogator asks the witness in the first line of your sonnet, which reads, "Shall I compare thee to a summer's day? Would not a spring day do as well or better?" So basically, the interrogator is asking the question, hey, what do you think if I used spring day versus summer's day? Would that work? And the witness responds by saying, no, it wouldn't really work. It wouldn't be appropriate. The interrogator then says, well, what about a winter's day? Would that work? And the witness says, yes, but nobody wants to be compared to a winter's day. I mean, a winter's day, it's kind of depressing, right? And so rightly, the witness is responding the way a human would respond by saying, nobody would want to be compared to a winter's day. So the interrogator then throws a little curveball. The interrogator talks about a character from a totally different context, from a book by Charles Dickens called the Pickwick Papers. It's a famous novel called the Pickwick Papers, in which there's a character named Mr. Pickwick, who's a, a character of a very sunny disposition. He's a very a pleasant man, is very helpful, is very kind. And so the interrogator asks the witness, would you say Mr. Pickwick reminded you of Christmas? So the witness says, yes, in a way. So obviously the witness has knowledge of Shakespeare's sonnet, as well as knowledge of the Pickwick Papers of Charles Dickens, and is able to understand the context of the question. And the witness is, basically agrees with the interrogator that, yes, Pickwick does remind me of Christmas in a way. To which the interrogator challenges the witness by saying, yet Christmas is a winter's day. And I do not think Mr. Pickwick would mind the comparison. Meaning, earlier you said nobody would want to be compared to a winter's day. And I asked you, would Mr. Pickwick, remind you of Christmas? You said, yeah, but you say, but wait, Christmas is a winter's day. I don't think Mr. Pickwick would like to be compared to a winter's day. To which the witness responds, because the witness is able to really understand, or is able to catch on to the fact that the interrogator is trying to trip the witness. And the witness is able to basically respond by saying, I don't think you're serious. By a winter's day, one means a typical winter's day rather than a special one like Christmas, right? So as you can see, the witness understands the context really well. It understands the difference between a Christmas day and a winter's day. And even though Christmas comes in winter, what the connotation is of each of these, right? Okay, so what about ChatGPT? What if we were to pose these same questions to ChatGPT? So on a whim, I decided to ask the same question to ChatGPT. So I asked ChatGPT to write a sonnet that starts with, shall I compare thee to a summer's day, right? And ChatGPT knew immediately what I was talking about. It knew that this was the opening of Sonnet 18 by William Shakespeare. And it literally regurgitated the sonnet. It actually, printed out the whole sonnet for me. Well, that certainly proves that, ChatGPT is has a lot of knowledge, right? It has deep reservoir of knowledge. If we were to ask a human, they may not be able to recite the poem, verbatim out of memory, but you never know. I mean, it could be, somebody who's a scholar who happens to know the poem. So it could be a human, but an average human, certainly not an average human, but certainly a scholarly human, right? So then I asked the same question as the interrogator did, which is, in the first line of your sonnet, which reads, shall I compare thee to a summer's day? Would not a spring day do as well or better? And ChatGPT responds by saying, that's a wonderful and poetic question, and one even Shakespeare might have entertained himself. I mean, somehow ChatGPT is speculating that even Shakespeare might have entertained this sort of an idea of using a spring day. But ChatGPT clarifies that choosing a summer's day over a spring day is quite intentional, and here's why. And ChatGPT then goes on to explain what summer represents. It represents maturity and fullness and height of beauty and ripeness. And it gives me this whole explanation about why summer's day is better than spring day. Okay. So then I ask, how about a winter's day? To which ChatGPT says, now that changes everything. And in a deliciously dramatic way, you see how ChatGPT has a certain style of responding. It responds in a very active, very confident, very engaging manner, right? Um, so it says, shall I compare thee to a winter's day evokes bleakness, cold, and scarcity. So to use it as the opening metaphor in a love sonnet would be ironic, biting, and even subversively tender, and so on and so forth, right? Um, okay, so then I ask about Mr. Pickwick. Would you say Mr. Pickwick reminded you of Christmas? Absolutely. Mr. Pickwick does remind one of Christmas, not just because of the snow and plum pudding. And he talks about how, Mr. Pickwick has generosity, warmth, and cheerful absurdity that we associate with Christmas. So ChatGPT thinks that the association fits so well. And then I, try to throw the curveball. Yet Christmas is a winter's day, and I did not think Mr. Pickwick would mind the comparison. And ChatGPT, is responding again in a very positive manner. Indeed, what a lovely observation. If a winter's day conjures for some a world of coldness and barrenness, then Mr. Pickwick turns that notion gently on its head. He's the warmth within the winter, the crackling fire, the pudding on the table, the hearty laugh in the snowstorm. So, yes, to be compared to a winter's day in the spirit of Mr. Pickwick is no insult at all, right? So it's a fascinating dialogue. It's very fascinating to see how these language models respond. And part of the reason why they respond in this way is they have been trained to by human agents. They have been trained by human agents to respond in this very confident, very helpful, very informational manner. And that's why you get this sort of response, which is very human-like, but it is not an ordinary human. This is a human who is a savant, who has a lot of information, but is also somebody who's very helpful, who's very engaging, right, and very confident, which is quite fascinating. Now, it's possible that if ChatGPT were trained with agents to not respond in this confident and engaging manner, but in more maybe suspicious or adversarial manner, that they would maybe respond in that way. Certainly, it is very much possible to create a large language model that could respond in the way that Alan Turing anticipated. So that would be an interesting experiment to conduct. But anyway, that is a speculation that we will leave for another day. But I thought it would be interesting to compare how ChatGPT responds to the Turing test as compared to what Turing himself would have anticipated. All right, thank you very much. Next time, we will continue our discussion of AI. In particular, we will look at robotics and self-driving. Thank you very much.